Hello, everybody. My name's Matt Swoboda, also in the demo scene I'm known as Smash Fairlight. By day, I work for Sony Computer Entertainment Europe in their R&D team, and my night job is coding for Fairlight. This is a rare opportunity for me, actually, to talk about our demos to a captive audience, so I'm going to start by bragging a little bit. So here's a potted history of our assembly productions. In 2005, we had Che Guevara, which won the 64K intro compo. 2006, we won the 64K intro compo, and we came second in the demo compo. In 2007, we had a bad year, and we came third in the demo compo. And we won the 64K intro again in 2008, and in 2009, we finally won the PC demo compo with Frame Ranger. Enough bragging, anyway. So I wanted to talk a bit about how we make our demos, specifically the rendering side and the visual side. So it's probably quite a tech talk, but hopefully it's not going to be too heavy. Firstly, I wanted to say why we make demos. Because why do we make demos rather than something else, like a video or a game or something like that? I think the key point about demos is that they're a technological medium. They should be technically innovative and impressive. I know there's debate about the art side and the design side, but the core of a demo is its technology. And I personally believe that every demo we do should be modern technologically. It should push things to the max. It's what sets it apart from like a pre-rendered video or a Flash movie or something like that. The technology is important. But at the same time, we're not making those NVIDIA tech demos either. We actually have to be stylish. The demo scene is the one place where you get technology and art put together, in people at the top of their game in both, working together to do something that's strong on both sides. So a demo should be artistically interesting, creative. It's not a video game that has to be realistic. It's not a tech demo. It's something else. But at the end of the day, a demo is about showing off. It's about showing off your talents as a programmer and an artist. It's not necessarily, I mean, there are other aspects to making a demo, like storytelling or soundtrack or the creative, the direction of it. But at the core of it, a demo is a technological piece. And that's why our demos are very tech-heavy. So this is how we make demos. We've got a team of usually just one coder, which is me normally, although there are 2 active coders on PC. But because our workflows are quite different, we tend to work on our own things. We normally have a large number of artists, and it's probably not fair to say how Fairlight make demos because we very rarely make a demo on our own. It's normally Fairlight and CNCD and Orange and Friends and whoever else was on the rocks at the time when we needed some graphics. So it's normally quite a lot of artists using a range of different tools and a musician. The thing that I think sets Fairlight apart in some ways from many other demo teams is that actually everyone working in the group is a pro in their field. So myself and Pantaluna are in the games industry coding. The artists are all professional 3D artists, or doing print work or motion graphics or animation or whatever. So we actually have a lot of resources at our disposal, but we're very limited in time. So we tend to have to push things out in a couple of weeks. We don't have these sort of 9-month projects like our Greek friend over there does. But we tend to push things out in a week or 2 weeks to a month. Very intensive. So it's a different flow. And so we work to support that, basically. We designed our workflow to support that and facilitate that. At the core of it is we have our own demo tool called Demolition Builder. This has been around quite a while, actually. It's quite a mature tool. We started probably this one in 2003, and there are elements of the code base that go back to 2000, probably. And since 2007, it hasn't really changed that much, just small things. The node graph and that structure appeared in 2007, and since then it hasn't really changed. So it's built on DX9 and MFC, which is not necessarily in vogue technology, but it's still working for us. The main thing about it is that it's completely plug-in based. There's a GUI, and you can plug in a completely different engine, effects, and everything. So we use it for everything. We've used it for demos, 64Ks, 2 issues of Zine Disk Mag were built on it, and we also do offline video stuff with it, using different plugins in the tool. So for that point of view, it's worked really well for us. But we're not one of these groups that makes a demo tool and gives it to an artist and bugs off on holiday for a month while they make something. We actually develop rendering and effects code all the time, constantly. So the engine is always changing. The tool is really the core of our workflow because it allows us to work, all of us to work together effectively. It's not just the coder seeing on his own. The tool is heavily built around Lightwave 3D. So much so that when we needed Maya support, I wrote an exporter to Lightwave rather than try and import data into like a new format. The animation, the transform hierarchy, a lot of the setup is heavily based on it mirrors Lightwave. And we support most of the stuff in Lightwave, including things like some third-party plugins that we hacked in, like emulation for. The reason we chose Lightwave is that pretty much all of our artists are using it all the time, so it made sense. The tool has 3 major views. It's got a node graph, a timeline, and a curve editor. So you see the node graph. This is, I think this is the node graph from Blunderbuss, which is actually quite a small and simple node graph. I think Frame Ranger had one scene with 10,000 nodes in it, which became a bit unwieldy. But this one is quite light. And it has a timeline, which is just the temporal view of the same structure. And then a curve editor as well, which is just keys on the curves. So this tool was quite a lot of effort and time. And it took a lot of investment of work, but it's given us some major benefits. I mean, the obvious benefit is that we have complete, what you see is what you get editing. You change a color in the tool, you change a parameter in the tool, and it's there, already changed. It drastically reduces the amount of time we spend changing code, recompiling, and running. On an ideal day, you would not change the code at all. And this is particularly helpful when a lot of the code is actually in shaders, and you can reload those at will. It means that the number of times you have to restart the tool is very low, which just makes things a lot easier to work with. A tool means that it's easier to manage a very large project with a lot of files because you can see all the resources that you've loaded. You can optimize unused resources. You can do things that, if you'd hard-coded everything, you'd actually have to manually look through your code and work out where you loaded stuff that you didn't need and remove it, whereas we can just click the optimize button and it goes away. The optimize button, yeah. So it's opened up the demo-making process to the whole team. It's like, instead of just a coder sitting there doing everything, while the artist makes some 3D graphics or something, it's actually the artist doing most of the work on the demo, while the coder is supporting and doing some of the work. It just means that it uses everyone's resources and talents so much more efficiently. The really interesting thing about a tool, actually, that I don't think people necessarily get before they've made one, is that the real benefit is what you get out of it that you didn't expect to get. So when you make an effect and you hand it over to an artist and they do something with it that you would never have thought of yourself, they change all the parameters so they're all completely wrong. And they mess with it with some mesh that you never would have put with it, and you get back something that was far better than you ever would have made yourself. And that's the real bonus of it. You get the creative input of everybody, and they see things in different ways. And they come at it from a different angle, so they add their own requests, and they can look at an effect and say, if this was slightly different, we'd be able to do this with it. And that's exactly what they do. So we get unforeseen benefits out of it. So talking about the technical side, the demo engine is a very, very large 3D rendering engine beast that its major goals were to be extremely flexible and still efficient. So this is really, I think, the goal of a demo engine, is to be flexible, to facilitate you making new stuff very easily and plugging it in. So my render loop in the old days probably looked like a lot of other people's render loops. It's like a big function that says things like, if motion blur is enabled, then do this shit with motion blur. And if SSAO is enabled, then add this render pass here and do this other stuff. And it became like this combinatorial nightmare of code. So I scrapped that, and we've moved to this kind of job model where it runs through the node graph, and there's like a list of passes, and each pass has a list of jobs, which are executed in order, and they can be sorted and stuff like that. So now the way it looks is that if you have a motion blur node in the graph, then the motion blur node adds a velocity buffer render pass into the list, and it adds a couple of jobs to post-process the velocity buffer, and it adds a job to render the motion blur process. So it means that it's completely flexible. If you want to add a new effect or something that hits like half the pipeline, you don't have to go and hack code into other places. You just make a thing that adds some jobs into the right place, and it's done. One of the major goals of the engine actually was to be transparent to the artist. The artist doesn't want to know that if he has to add a shadow, he has to do a render to texture and to a depth buffer and create that depth buffer and all this kind of thing. He just wants to add a light and turn it on. So it's completely transparent to the artist. The engine works out what it needs to add based on the nodes and sorts it out. When it comes to 3D rendering, we have this quite a heavy engine. It supports both deferred and forward rendering. Does anyone know what I'm talking about when I say deferred and forward rendering? Yeah, lots of nods. That's good, because this would make no sense otherwise. It's a reasonably good implementation. The deferred rendering has like unlimited light support. And one of the best things about it actually was that all the geometry buffers, the depth, the normals, and this kind of thing, proved really useful for quite a lot of effects, which we'll get onto later. But we also have a forward rendering path which still gets used for the alpha stuff, so it can't be rendered deferred. But we rarely used it. We used it up until about 2008, I think. One of the main features of the rendering engine is the Uber shader setup. Has anyone used Uber shaders before? Put your hands up. Oh yeah, Ceasefire, of course. Yeah. So Uber shaders is basically, you write a shader and you have shitloads of if-defs all the way through the code. Like, if-def motion blur, then do this code in all the fragment and vertex shaders. And then in the engine, it works out what's active in the scene, and it calls compile on the shader with the set of if-defs you've passed in. So if motion blur is active, it recompiles the shader to add the bit of code in that does the velocity output of the calculation. So you only have to write one big shader, and you get thousands of shaders out of it, but they're all optimal for the situation that you need. So you're not carrying around this vast weight of unnecessary shader code, and you're not carrying around 1,000 shaders for every. Like, you don't have to write a special shader that does 3 lights and 1 shadow map and motion blur and all this kind of thing. You just have one shader, and it compiles the right version of it. And this is pretty old technology. I think they've used it in Half-Life 2 and many other games, but it's meant that our rendering engine is even more flexible, because we actually only use one shader pretty much for the whole demo. But it's just if-def different sections. So if you want to add a new feature, you just add the new code, add the define, and get the engine to compile it. It means that doing things that hit like the whole engine, that need a new render pass with different data output, with various post-processors on that data, different buffers, you can accomplish it very easily. And I think that's the great success of our engine, is that it facilitates experimentation. I think that should be a goal of any demo 3D engine. So now what I'm going to do now is I'm just going to go through a few scenes from various demos that we've done, and just show how they break down, how the different passes are set up and stuff like that. The first one I'm going to show is this project actually never came to anything. I did it earlier this year, and we never ended up releasing anything with it. But essentially, it's a horse running through a desert landscape. And the reason I'm showing you this actually is because it's got quite a lot of passes, basically. It makes for a more interesting breakdown than just a model in an environment or something. So yeah, so the horse, start off with the environment. And I started by modeling quite badly, actually, some mountains in Lightwave. And I imported them into the engine. And I got a white screen. So I added a texture to it. And then I added a different texture to it. And I blended the textures. Actually, one thing I experimented with on this was deferred texturing. So it renders the geometry into G-buffers, and all the textures are done as full-screen passes later on. This means that you can be much more flexible with your lookups, and you can do some ugly stuff in it as well. I generate some height values by, I just put them in the alpha channel in Photoshop, and just rendered them. I picked up the alpha channel of the normal buffer. And I compute some parallax mapping, so you can see the differences like that to that. It makes it pop out. That was done with like raycasts through the scene. One of the advantages of deferred texturing is it makes big, heavy shaders definitely only get run once per pixel. You don't have to worry about geometry overlapping and this kind of thing. We calculate normals on that buffer and then use that to do directional lighting. And then I combine all that together. So I've got like a lit parallax map desert, which is reasonably close to the end goal. Could have used some AO or something, but this is all right for the basics. And I had the mountains in the background. Then I wanted some grass, so I generated some grass in code. A lot of our effects are very heavily shader-based. The CPU side is quite simple. So in this case, the CPU side generated a quad strip and a list of instances. And the shader did all the bending and wind and that kind of thing. One of the advantages of shaders is they're so easy to tweak. You can just keep reloading them and seeing the results on the fly. So it makes your workflow much quicker. So then I spread those randomly over the ground and put them in the, put them on the mountain, on the grass. And they're casting shadows as well, as you can see. Then, yeah, to make stuff cast shadows in our engines, you just have to put it in the list and it gets done. It's quite nice. And I added a sky dome, and I added the distance fogging. And then I moved on to the horse. Horse started off life in Maya by an artist at work. And thankfully, I had written that Maya to Lightwave exporter, so I could export it into the engine. So when I loaded it into the engine, it looked like this basic gray horse. So I added a bit of lighting to it. And then I added a fur shader, which is also running deferred. It's a lot easier. Again, it's a good use of deferred texturing with raycast to get the to step into the fur. Yeah. Sorry? No, I cheated. I just have like a map saying where the hairs are, and I just step along the ray saying it's the same thing for every pixel. Yeah. Feel free to ask questions, by the way. Then we started working on the hair simulation. So the hair simulation is particle-based, actually. It's just all the vertices are particles. They're arranged in, simulated on the GPU. They're arranged in such a way that I can look at the neighbors along a hair and do a spring simulation. So it's just a small extension to my existing particle system. And they're drawn as splines, just all done in the vertex shader. And then, so we stick the hair on the horse. And then we add lighting to the hair. The lighting is same lighting as I did for particles, which is using opacity shadow maps. It's a good way of doing shadow maps for alpha stuff, basically. We'll get on to lighting of particles a bit later. Then we stick the horse in the environment, and stick the shadows on the horse. So now the horse actually looks like it's kind of part of the scene, which is nice. And then finally, we add the post step. So this is what the importance of post-processing is like, very obviously demonstrated by that. It's like color correction, some little bits of glow on the sky, that kind of thing. Small things that make a big difference in the final result. I think I have a video. Hang on. See if this will work. I don't know if this will work. Yeah. Hang on, is it doing it? No. Oh, there you go. Sorry for the ad hoc technique, but there you have a horse. Not particularly great animation on the horse, but the technique is there. The next shot I wanted to show was a shot from our breakpoint demo this year, Agenda circling forth. The flowers scene in that demo. Has anyone seen that demo? Yeah, a few people have seen that demo, cool. So Agenda was entirely built from particles. We had this GPU particle system that does like, it can do 1 million particles a frame reasonably comfortably on good hardware, on very good hardware. Yeah, we're getting better over the year. So the big thing about a particle system actually is that it's very easy to do a big particle system on the GPU. What's difficult about it is getting the control and being able to emit from interesting sources and being able to light them nicely and animate them nicely. It's not so much about the numbers, it's more about the level of control that has to go into it. So in this case, in Agenda, we're spawning particles from meshes, images, and also using G-buffers. And for the meshes, we can use the animations on a scene to update the particles, make them flow. We also sort the particles on GPU using some odd-even merge sort, which NVIDIA have released, actually. So if you want to find that, you can find it. And lighting uses opacity shadow maps. Is anyone familiar with shadow maps? I'm coming out like everyone is, it's cool. With a shadow map, you render just the depth of stuff into a buffer. For alpha stuff, you can't do that. So you render a load of slices aligned along a volume in view space. And at each slice, you have a depth value, and you render the alpha value of the thing you're rendering at that depth. So if you have a particle, if it's further ahead than your slice, you render nothing. If it's on the slice, you render the alpha value, basically. It's pretty simple. And then when you apply it, you just find the slice closest to where your pixel is in depth space and sample the value from that and interpolate them. So you get this alpha shadows, basically. We also we have fluid dynamics used quite heavily on the particles. We use this curl noise technique, which is like a way of faking fluid-like animation using derivatives of a noise field. So you get this it's quite a nice look. It's done by Robert Bridsom. And that was used for a lot of it, but we did also have some actual proper fluids with Navier-Stokes, which were evaluated on the GPU. So let's go to the scene. Here's how the scene looked in the end. It's quite funny, actually, because it's not very obvious what it looks like until it's in motion. But so that's how it looks. Starting with the environment. The environment was emitted by rendering mesh into G-buffers. And then in screen space, you back project the screen position with the depth value into world space, and that's where you put the particle. So the particles are emitting essentially in 2.5D, if you like. But it means that you get very good coverage for all your particles. If you emit from meshes, you tend to get all the back faces, the interior faces. It's very hard to get a lot of particles on the screen. With a screen emitter, you get a thin slice, but very well spread. So we render the mesh into the G-buffers, and it's got SSAO on it, actually. I don't know why, but it has. It was quicker than baking it or something. And it's got texture and everything, and it's also got some dynamic lights. So it's just all the composited deferred render is used as the particle color. And when you turn it into particles, it looks like that, which is, the screens don't match up, but it's a reasonably faithful representation. Then we put some fluids on it, so we start actually animating the particles, and you get this nice, quite abstract look where the particles are spawning in and moving and dying off, but it's quick enough that the form is still reasonably obvious, but at the same time, it looks much more interesting than what you could do with a mesh. It looks almost solid, but still not quite. Then we did the flower. The flowers are meshes. We use meshes because they're animated, and they're animated just with skin and bones from Lightwave. And the particles, when we emit from a mesh, we pre-generate a big buffer, which works by finding the total area of all the polygons on the mesh, and then evenly distributing particles on all the polygons, and just storing them in a big texture as position values and color values. And we also store skin weights and skin bone indices, so we can run the same skinning process that you do for a mesh for particles, like for every particle. And you can, when you come to move the particle, you just run the skin and find out where it was last frame with the skin, and you just update it accordingly. So when they're rendered as particles, they look like that. These, I don't know if these are proper screenshots. I think I did them on my laptop, so they're not quite as dense as they should be, but that's roughly what you get. You get a flower with some, all made from particles, which animates nicely as you go. And you stick them together, and you've got like the flowers out on top of the tree, and the sorting sorts out the order. Then do a bit of color correcting, fix the background color, fix the lights a bit, and you get something that's a bit more reasonable. Then we just did like a sky dome and emit like a lot of low-res particles. We actually just didn't use blob textures like you'd expect. We got some rendered out like video kind of, like, you know, when you see on some old videos, you see like these blobs that are like where there are bright lights and stuff. We got a load of those instead of using just plain discs, because it had a lot more interesting look, and they had slight discolorations and shapes which worked really well. And we had them all in a big texture strip, and it just picks randomly from that by offsetting into the strip for each particle. And when you put it together, you get this, this. You get particles with the backgrounds, and then the magic post step. The post step always makes a huge difference. In this case, it's color correction. There's like a halo kind of vignette on everything, and it gives you the final image. The final shot I want to show, oh yeah, if you want the video of that, I don't have one, unfortunately, but and it doesn't run on my laptop either, the demo, but you can download it, it's fine. The final shot I want to show is it's a scene from the demo we're releasing tonight, so we'd appreciate it if you didn't let the information travel out of this room, if possible. This is on TV, isn't it? Never mind. Oh, can you edit this part out? All right, yeah, anyway, it doesn't really matter. Anyway, so yeah, here's the shot breakdown from this street scene. So we made a street out of buildings, and we wanted the street to explode buildings one by one going down the street with like these time-stretched explosions. So it's like each building explodes, and the explosion starts fast and it slows down, and then the next building explodes. So it's like a design-ish kind of exploding street. So we needed quite a lot of particles. This scene actually ended up with 10 million particles per frame, which I think is a new PC record. Do we get a medal for that? So here's the initial shot. This is all particles. It's completely, it looks quite solid actually, doesn't it? But it's, yeah, it's all, every building contains 1 million particles, and there's like, and the street and the lampposts and shit. So there's like, each building going down the street is 1 million. and we needed to explode them one by one. So we got the mesh in Lightwave, which is just a big scene that Yanni built and baked. And then here's one of the buildings. So the mesh isn't too dense, actually. It's just it doesn't really matter for particles anyway. And then we had to particleize it. So when you so you've got each of those. So that is probably the size of one building that in the scene as 1 million particles. So we got how do you manage 10 million particles given that agenda wasn't all that fast and it only managed 1 million? Well, smoke and mirrors, basically. It's a lot of cheating. So first thing, when we started doing this shot, we thought, all right, how can we get this many particles? We looked through it, so we thought, is it that rendering a lot of particles is slow? Or is it all the operations that get done on the particles that makes it slow? So we did a bit of a breakdown of the engine. So 1 million particles is a 1024 squared buffer. It's actually several buffers. And typically, you need to do an emitter and then some effectors, and you can do displacement maps on it as well. And then you actually update the buffers. So you update the lifetimes, move the positions, update the velocities, update the colors. To do all that typically is something like 10 passes over a 1024 buffer in a frame. It's a bit more than that if you have more effectors. And some of the effectors are almost nothing, and some of them, like the curl noise, are like 900 instructions or something, so they're quite heavy. One problem is the speed. The much bigger problem is the VRAM, because all those buffers, you need the current state and the next state, and we also store some other state, just for effect reasons. It ends up that for 1 million, but I mean, think full float buffer. We have to store the particles as full float because we lost too much precision with half float. So for a position buffer for the particles is 16 megs for one buffer. And then you've got color, velocity, some other information. You need buffers for lighting, for sorting. You need the previous state as well. And you need some intermediate buffers. When you add it all up, it's something like 100 megs of VRAM for 1 million particles to update them and store their state. And if you've got 10 pieces of those and a 1 gig card, you're kind of on the edge. So it was already proving problematic. It's more the memory was a bigger problem. Yeah, and then the next stage of the pipeline is the lighting and sorting and rendering. The lighting is not that bad because it's just applying 1 pass per light. The sorting was very painful. An odd even merge sort, it's not linear with buffer size, but it takes 210 passes to sort 1 million particles. So 210 passes over a 1024 by 1024 buffer. It's going to take quite a long time. So we split that over 10 frames, 21 passes a frame, and so it gradually becomes sorted. It's not imperfect. It's not perfect, but we don't really care. It works well enough. So that sorting stage is one of the heaviest stages. And finally, the render. You just render all the particles as point sprites. So it's 1 million point sprites. So let's get to optimizing. At the initial state, all the buildings are pretty much static. So you don't have any effectors on them at that time. All they're doing is just spawning and animating lifetime and fading out and respawning. So if there's no effectors that are active, you don't need to actually move them. So you don't need all the update buffers and update steps. So that saves loads and loads of memory. We just need a static position and a static color. And we can do some tricks to fake the fading and fading out of a particle. And we don't need to do all the update stages. So we saved ourselves tons of VRAM with that. We wanted to still be able to move them, even though they're officially static. So we did some like displacement mapping. It's basically like render time animation. So for example, it doesn't require state. It's seeded off the current position. So for example, use a Perlin noise to animate the particle, just using its position as a state. And you can give it like an animation without having to ever move the particle in the buffer. So we can give them a bit of movement. just done at render time. You can do it in the vertex shader even. We wanted to avoid sorting, so we knew that we were roughly going to be looking at them from one axis. So we pre-sorted the particles in the emitter buffer, so they come out already sorted for the camera. So that got rid of the sorting issue. And finally, we didn't want to light them, so we baked lighting in. If they're static, you can bake lighting. And finally, if they're quite static and the camera's quite static, you can use an imposter and not render them at all, which is quite nice. We'll get to that in a minute. So, yeah, so here's how the shot was done. 10 million particles actually does get rendered in the initial shot, but they're all static. So all they're doing is sampling from static buffers, doing some small render time displacement on them, and rendering them to point sprite. So it's effectively one pass for that whole thing rather than sort of 40 or something that we needed to do it with animating particles. The buildings, we've done the shot, so the buildings explode one by one. So when the building explodes, we switch it from static to dynamic particles, do the effect on it, and it's only dynamic for the time when the effect is active. And the explosion is cleverly time stretched for design reasons, but it also means that at the end of the explosion, the particles are moving very slowly, so they're almost static, so you can almost go back to static. The problem is that even though we don't need to update them at the end state because they're not really moving, we still need the memory for the other buffers. It's more of a memory problem than a performance problem at this point. So when they finished exploding, we switched them from particles to an imposter. So you just render the particles and blend that in the right sort order. But that would mean they're static, which isn't that nice. So we did some small faking to make the sampling of the imposter still update like the particle was moving. So it's an imposter that's slightly dynamic for slow-moving stuff. So now you can imagine the way it works now is like buildings are all static. A building explodes and turns into dynamic particles. And then at the end of the explosion, when it's almost time-stretched still, it switches to an imposter, which updates very slowly. And then the next one explodes. So we wanted to control the explosion a bit, so we stuck a weight map in Lightwave, which just controls roughly the times when stuff explodes. So the more red it is, the later it gets, the particle gets exploded. It gives you a nice variation, so the windows go first, and then the rest of the meshes come later. And then the next explosion starts. So you got this like, so that one explodes, and then the next one starts exploding, and it's carefully synced so that the buffers get allocated, exploded, imposters released, just in time, so everything doesn't run out of memory and crash, which is nice. So yeah, with this shot, it worked out in the end. No, I'm not going to show a video. Yeah, it was. Now, the thing with this shot is, you might look at that shot and think that is overkill for what you try to achieve. And in a way it is, but I think the point about demos is that it's not just about faking an easy result. Demos are a technological medium. It doesn't always matter that what you did is overkill. What matters is that technologically it's cool and you presented it in a cool way. And maybe you actually ended up doing this massive effect, like the fluids at the end of Frame Ranger. We did this massive effect, and then it got optimized out by the artist, so all you could really see was not all that much, but it looked nice stylistically. And technically underneath, there's something cool going on, even though it's not presented like a tech demo and shown. We don't need to show things like you can go through and count all the particles. We want to show it like it's cool and there is technology there. We're not in the business of making easy stuff, flash animations or simple effects and making them look nice. It's fine to do fakes and simple things, but if all you want to do is fake something, you just render out a video and play it back. That's faking, and it looks good. in the end, I think with a demo, you need to do something cool and know that underneath the technology behind it, it was there as well. You can stand up and say, we had this nice piece of technology as well, and the end result looks cool. And you can be satisfied knowing that there is technology under there, but it still looks cool at the end. It is the final result that matters in the end. It's what's on screen, but in a different way, it matters as well how you got there and what was underneath it. And that's me done. Is there any questions? I draw your attention to the small message on the bottom right. Anyone got any questions for me? No? Are we early? Yeah, a little bit. Go on. What's that?
Did you bring your own machine to run the demo?
No, we're using the 480, it's fine. Cheeky. Yeah, we have a render farm with us. Any other questions? No? All quiet? That's cool. Does anyone want to know anything else about what we've done? Or is it? It's open to the floor if anyone has any questions about anything we've done or any specific effects or anything. We've got time to kill. Yeah.
Hello. I'm interested in when you said about making a new effect on the shaders, and you store the data in the G buffers and all that stuff. I think that space is limited. And how do you manage if you are running too many effects to the Uber shader and you run out of space to put all the intermediate data for the deferred rendering? How do you manage that problem?
Well, the G buffer, the size of the G buffers in memory, you mean?
Yeah.
It's not too bad actually, because a G buffer is something like, so if you've got a depth buffer, it's like 4 megs for a 1280 by 720. And you can keep quite a lot of that around. We have quite a complex render target VRAM management piece of code, which lets effects like lock and unlock render targets, so they can all share everything. We used to just like have every effect would statically allocate a render target and keep it to itself, and we ran out quite fast. So now we have this VRAM cache management thing, which lets effects share and manage render targets quite efficiently and transparently. And we have a small issue with the current demo, actually, in that we're blowing the VRAM limit on regular consumer cards. So we had to do some garbage collection and stuff. But VRAM is actually one of the biggest problems we have at the moment. Memory in general and VRAM. Every demo we've done recently is hit the Win32 app limit on memory and come very close to the VRAM limit. So we're looking forward to the days of 4 gig graphics cards and 64-bit OSs.
Okay, hi.
Yes, hello.
Hello.
Please introduce yourself to the room.
That's okay. You talked about sorting those particles at some point, and it takes quite a few frames, because I understand there's quite a lot of calculations. But can you tell us, why do you need to do this sorting in the first place? I mean, they look that they are not transparent, and they look like they couldn't you just use the Z buffer? And
they're transparent.
They
fade in, fade out. So if you use Z buffer for alpha stuff, you would have stuff being not there and obscuring other things, which would be very bad. We actually, in this demo that we've done, actually, we went to massive lengths to avoid sorting wherever possible. So the emitters, if you have 4 emitters in the scene, like a screen, like a G buffer emitter and a mesh emitter and something else, then we sort the emitters so that they appear in roughly the right space in the render target. So you can minimize the requirement for sorting. Because, yeah, as you said, it's a big problem.
Okay, so basically the only issue is that you have transparency on the particles, or some particles, during the beginning and the end phase of their life cycle.
Yeah, or the middle. Yeah, the middle.
And the middle.
The middle of their life cycle. Yeah, they can all be. They normally have an alpha of about 0.5, but because they're quite dense.
Okay, but have you actually tried to see how they look like if you
With
put
Z-buffer?
if you put the opacity to 1?
Yeah, we've tried it with Z-buffer and alpha to coverage, and it didn't look all that good.
Oh.
Actually, we tried this, just diverging in the moment. One thing I've been doing a lot of recently is trying to get our demo engine usable for video projects. So you don't care about the render time being like 10 seconds a frame, but it's still better than rendering it offline for 10 minutes a frame. And that, we've been doing, like for starters, we can perfect sort because we don't care how long it takes. And secondly, I did this thing where you render really, really high-res buffers with dithered alpha. So like you have the more alpha it is, the more noisy it gets to nothing. And then you just downsample and interpolate. And it looks a bit closer to...
Okay, I don't want to give you any ideas, but have you ever tried to do some sort of a morphing between two sets of particles, one representing, let's say, your horse on that cracked earth with the grass, which doesn't grow actually on cracked earth, but anyway, grass. But to make into something.
I'm sure I've seen cracked earth with grass on it, just a little bit poking out of the ground.
Okay.
Yes, actually, there we have two. One emitter we have is one effector is a mesh morphing thing, so particles can be attracted into another mesh. But something that we did for this one was we're using distance fields. So you take a mesh and a volume texture, and you generate in the volume texture the nearest, like the distance to the nearest point on the mesh or the nearest face. And you also store the color of the nearest thing on the mesh. And then you can literally just find the closest thing on it and attract the particles to that and change their color as well. So yeah.
Does that guarantee that there will be a full coverage? Because with this situation, you could end up having holes.
Yeah, you can get some holes. Yes.
Or even worse, I don't know, correct me if I'm wrong, you could get some cyclic movement.
No, the cyclic movement's not a problem because the distance field stuff does work. But what you tend to do, one of the things about when you have shitloads of particles, like 1 million particles, is that randomness, there's some theory, isn't there, that if you generate enough random numbers, you'll get all the numbers, if you have enough of them. Well, it's kind of like that for particles. If you use rand in the right way, then if you apply small random offsets to where something's going to, in the end, you'll get close enough to full coverage. Yeah.
So now that we are talking about distance fields,
yeah,
pretty off topic, but did you ever consider using kernel noise as a directional field for ray marching? Because I read the same paper that you read, and
no, I never tried that. It's interesting though. We've used Perlin, but not kernel noise.
Okay, but
Hang on, let me write this down.
I have this project that I'm developing that uses kernel noise as a directional distance.
And how does it look?
Shit. So far, it looks like shit.
That's very encouraging. I'll try right away.
But yeah, it might be of interest if you're dealing with particles especially.
Kernel noise is very useful. It makes everything look slightly better. Try it out.
And, okay, one last question. When are you going back to your traditional triangles and stuff?
Triangles? There's no hurry. We've branched out beyond particles now. We have other effects. We have more than just particles. We have some lines, I think. We're building up to polygons. Maybe next year. Yeah, I think are we out of time? Oh no, we have a question. Oh no, I have 2 minutes. No, we don't have a question. We just have a wind up. Anyone else? No? Cool. If no one else has a question, then we're good. Then we're all done. Thanks a lot.